Hi folks. Today we're going to learn a bit more about the periodic table, its history, its layout, and how that relates to electron configuration. So, the periodic table was developed to organize all the elements that had been discovered at that time. And Dmitry Mendeleev was responsible for coming up with the first periodic table. Basically, he noticed that certain elements had similar properties. And so he arranged the periodic table so that all of those elements with similar properties were in the same column of his periodic table. He noticed that when he put elements in order of increasing atomic mass, these repeating patterns of properties appeared among the elements. And these repeating patterns, this is called periodicity. Periodicity. Something that's periodic has a repeating pattern. So this repeating pattern is called periodic. This is why in our school schedules, we say first period. First period is always from 8:30 to 9:50 every day of the week. It's a repeating pattern. So Mendeleev is credited with discovering the periodic law. When elements are arranged in order of increasing atomic number, elements with similar properties appear at regular intervals. This is the periodic law. Now notice, Mendeleev didn't say anything about atomic number. He put his periodic table in order of atomic mass. This is because protons hadn't been discovered when Mendeleev was organizing his periodic table. So there was no such thing as atomic number. But our modern understanding of the periodic law involves atomic number. And so we credit Mendeleev with this property even though we modified it with our modern understanding of the number of protons defines the element. The cool thing about Mendeleev is he left gaps on the periodic table where he thought new elements would be discovered, and he was right. This is part of the scientific process. If you make a hypothesis based off of facts, then your hypothesis should be able to make predictions, and then those predictions can be tested. And in this case, Mendeleev's predictions were tested, and he was correct. Moseley is also an important scientist in the history of the periodic table. He gave us the modern periodic table because in 1913, that was just a couple of years after protons were discovered. And basically, as soon as protons were discovered, Moseley said, hey, elements fit into their patterns better if we arrange them by atomic number, not atomic mass. So this is how we started to notice that it was the atomic number that really defined the element. If you look on your periodic table and compare iodine and tellurium, you'll see that the order based off of atomic mass is different to the order based off of atomic number. So this was an important development for getting elements into just their right positions on the periodic table. And this is still the periodic table that we use today. So this is what our periodic table looks like. We've said before we have an S block, a P block, a D block, an F block. We've got color-coded elements. You guys have colored in your own periodic tables. The colors all mean something. We're going to go through those bit by bit in the near future. But for now, we need to have some basic vocabulary. So the vertical columns, those up and down columns of elements, are called groups. They're numbered 1 to 18 from left to right. So looking back here, 1 to 18. Each group has its own number. Elements in the same group have similar chemical properties. So they are like involved in the same kinds of chemical reaction. Whereas horizontal rows of elements are called periods. Horizontal rows. So those are the ones that go side to side like this. Those are called periods. Those are numbered 1 through 7 from the top of the periodic table to the bottom. And the physical and chemical properties here change somewhat regularly across the period. So what's up with those two rows at the bottom of the periodic table? The lanthanide and actinide metals are placed below the main periodic table, slightly out of order, just so that the periodic table will fit on one page. This is what the periodic table would look like if we put the lanthanide series and the actinide series in where they belonged on the periodic table. And you can see that we would have a very wide periodic table that we would have to print very small and you wouldn't be able to read it. The lanthanides fit into period 6 and the actinides fit into period 7. So, if we focus on group 1, the first 4 elements in group 1 are hydrogen, lithium, sodium, and potassium. So if we write those electron configurations, we've got 1s1. If we write the electron configuration for lithium, we have 1s2, 2s1. Writing the electron configuration for sodium, we have 1s2, 2s2, 2p6, 3s1. And writing the electron configuration for potassium, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. What do all 4 of these electron configurations have in common? They all end with S1 in their electron configuration. They all have 1 electron in an S sublevel in their electron configuration. If we do the same thing, for instance, for group 14, carbon, silicon, germanium. What do those electron configurations have in common? All of those electron configurations end with 2 electrons in a p sublevel. It's these similarities in electron configurations that give carbon and silicon and germanium similar chemical properties. Similar electron configurations means similar chemical properties. This aspect of the electron configuration is why we named these blocks on the periodic table S, P, D, and F. These 4 blocks on the periodic table have those names because the electron configuration of the elements in those blocks end with that sublevel. So the name of each block is determined by the last sublevel filled in the electron configuration. So hydrogen, lithium, sodium, potassium, those all ended with S electrons, so they're all here in the S block. Carbon, silicon, germanium, those all ended with P electrons, that's why they are here in the P block. Therefore, you can work backwards to determine the electron configuration of elements. And this can be extremely handy because you can know how the electron configuration ends without writing out the whole electron configuration. When you use the diagonal method, you have to write out the whole electron configuration. But if for some reason you don't need the whole electron configuration, this is a good shortcut. So, the block tells you what sublevel the last term in the electron configuration will be. The period, which horizontal row you're in, remember horizontal rows are side to side, that tells you the highest main energy level in that atom, the highest main energy level that will actually be holding electrons. I said this in the previous video, but knowing the main energy level for the sublevel gets a little bit complicated. If you're in the S or the P block, then the period tells you the energy level. The period tells you the energy level. If you're in the D block, you have to subtract 1 from the period. in order to get the correct energy level for that D sublevel. If you're in the F block, you have to subtract 2 from the period that you're in order to get the correct energy level of your F block. Lastly, the column of the block that you're in tells you the number of electrons that you will have in your last term. So let me show you what that looks like. Lithium. Lithium has 3 electrons, and it's in this position on the periodic table. It's in the S block, and it's in the second period in the S block, and it's in the first column of this S block. Therefore, the lithium electron configuration is going to end 2s1. The second period, the S block, and the first column. So there's just 1 electron in that S sublevel. Once I know that, I can fill in the previous pieces of information. I can fill in any previous sublevels to help me write the starting part of the electron configuration. Okay, so that's the example for lithium. Let's try another one. Let's try selenium. Selenium has 34 electrons, and we find it here on the periodic table. It's in the P block. It's in the 4th period. So I have to write that it's in period 4, the 4th energy level, and we're in the P block. Lastly, we count which column it's in. Column 1, 2, 3, 4. It's in the 4th column, so we say it has 4 electrons in that sublevel. Now we fill in the rest of the early electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. So we were able to figure out the last component of the electron configuration and then fill in all the electrons before it. Remember, you can use the periodic table or the diagonal rule to help you fill in these earlier sublevels in the electron configuration. The 1s, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, and remember you have to subtract 1 from the energy level to get the correct energy level for D sublevels. So after 4s comes 3d and then 4p.